Hey everybody, welcome to lecture 20. This will be our second lecture we're going to do this way on YouTube to get us through the rest of this week. And I will see you back in class in West Lafayette on Monday, and we'll review for our test. So about that, let's go ahead and talk about the things we have to do for this week. You have participation quiz 11 is open right now, and it closes on Sunday at 11:50, and it's your last one. It's about two ANOVAs. It's 4 little questions about that. Homework 9 opens today. It's about simple linear regression, but it's not due until a week after the test, so you have plenty of time. No need to start on that. In fact, I would not start on that. I would use my time this week to study for your test that's coming up and study the review material that's in Brightspace. But about that, test 2 is on Monday, April 4th, 8 p.m. in Elliott Hall. Same procedures as before. You'll sit in the balcony, sections LB 1, 2, and 3. There's a map of that in Brightspace if you forgot, but we're in the upper balcony area on the left of 3 sections. Be sure to sit there, and also be sure to turn your test in there so we can look at your test. A few of you failed to do that, and it was tough finding your test. Bring your one-page handwritten front and back with all your little notes and cheat sheet on it. And a calculator and a pencil. Don't forget those 2 things. Check Brightspace for the review materials, and then there'll be a review session on Monday just before the exam. I talked about that on Monday, and there's an announcement about that in Brightspace. There's also office hours on Monday, and I'm going to do like I did on the last test and hold those at 11:30 in our morning classroom in Walk 3090. Again, that's posted in Brightspace as an announcement. And if you are taking the test for the DRC, you need to make sure you schedule your exam as soon as possible. All right, so we're going to go into, I'm going to jump right into this and try to make this short and sweet. This is going to be a continuation of what we did on Monday. And so, simple linear regression so far, we want to study the relationship between 2 quantitative variables, x and y. And so we have an ordered pair for each unit. So x is our explanatory variable and y is our response variable. So the example I gave on Monday would be exercise having an impact on cholesterol. So exercise is the explanatory variable, and our response variable is the cholesterol. So the more we exercise, the lower our cholesterol is. And so that's what we call an inverse relationship or a negative relationship. And we're going to talk about that down here. So when we do a scatter plot of our x's and y's, we look for 3 things. The form, is it linear? It could be quadratic. It can be other things, but we're going to focus just on linear. The direction, is it positive or negative? And the strength, is it weak or strong? And so we talked about if r is greater than 0, it's a positive association. If it's less than 0, it's a negative association. So the example I gave of exercise going up causes cholesterol to go down, that's a negative relationship or negative association. And then if one thing goes up and the other thing goes up, such as height, if height increases, your shoe size increases, that's a positive association. And if the absolute value of r is close to 1, it's a strong pattern. If it's close to 0, it's weak. And remember, when it's close to 0, the scatter plot looks like you shot it with a shotgun. It's just the dots are everywhere. And when it's close to 1, the dots kind of follow a line. All right, so if we have a linear pattern, we can do a regression line, and we can do our least squares method to get that. Where we do this, there was a calculation we talked about how to find the equation of the line, the slope and y-intercept of a line that goes through those points in the most effective way. So we're going to talk about a few things related to that today. So we'll just jump into it rather than go through all of these bullets. So prediction is when you use that equation I just talked about, the y equals mx plus b, or remember in this case, our textbook uses y hat equals b0 plus b1x. You can use that regression line to predict the response for some specific value of the explanatory variable. So if you've done one with exercise and cholesterol levels, and you know that the more someone exercises, the lower their cholesterol goes, you can say if you exercise 47 minutes every day, your cholesterol, I predict, can be 187, or whatever the number is from your predictor. All right, now what you can't do is do extrapolation. You cannot do this because that's when you say, look, I know exercise ranges go from, say, 0 minutes all the way up to maybe 120 minutes. Anybody who exercises more than 2 hours every day there's people that do that. People training for marathons, for half marathons like I am, might run for 2 hours a day, but most people do not. And so let's say you try to predict what someone's cholesterol will be if they exercise for 3 hours a day, and your data only goes from 0 to 2 hours a day, then that's what we call extrapolation, and we can't do that. and so we can't do prediction for outside the range. So here's an example. This is what we did on Monday. We talked about this bone strength study, and so these are our actual x's and y's, and our y hat over here would be our predicted values for those response variables using this formula that we derived. And so these predictions are reliable. We can predict 12.5, we can predict 18 and 25 because our smallest and largest x values are 12 and 25.2. What we can't do is say, what if our x was 0? That would predict a value of 2.74. What if our x was 100? And you might not know anything about bone strength, but it looks like bone strength. I don't know anything about bone strength. You might recognize that, is it even possible to have bone strength of 100, right? It looks like bone strength numbers go from somewhere in the low teens all the way up to somewhere in the mid-20s, but not any higher than that. So anything you do outside of 12 and 25.2 is called an extrapolation, and that is not reliable. A residual is the difference between the observed value and the predicted value predicted by the response. So we do this residual E, and we take our actual y minus y hat. So if I go back a slide, let's say right here, we said if someone had a reading, let's say 12.5, and we got 12, this is not exactly what we're trying to say here. Here's a 12.3. The y was 12.9, but we predict it to be 14.254. The residual is the difference between those two numbers. So we predicted 12.9, but it was actually, we had an actual reading of 14.25. That's our residual. And a residual plot is a scatter plot of these residuals against the explanatory variable x. So if we take our table and continue it one further and do the residual, we're going to take the difference between the y and the y hat. And so 16.3 minus 17.4338, we get this negative number here. And so this residual plot takes all our x values, 15.7, and plots a negative 1.1388. So I'm guessing that number is about, it's probably that one right there. Right, that's that point right there. And so we're going to plot this x value against this residual number. And the residual plot should be a uniform horizontal band of points centered at 0 with no visible pattern at all. All right, so they're just kind of, again, just kind of splattered out there, just like you took a paintbrush and just splattered some paint on the thing. So you look at residual plot A, and that's kind of what that is. That's a good one. But you see this one has a pattern. It looks like it's almost quadratic. And so we probably made assumption that something was linear for residual plot B, and in fact the relationship was quadratic. And we talked about quadratic examples might be if you're testing a parachute and you drop the parachute down and you measure the velocity of the object that's falling, that's a quadratic relationship. And if you try to assume that that's linear, you're going to find out that it's actually not. All right. And residual plot C looks good. Again, it's kind of scattered evenly on both sides of the x-axis there. And residual plot D is bad. It's just because it starts out small and it's getting larger the further you get out here. So this one can be explained away by the mathematics of our assumptions. This one also probably is the same thing, but there's something strange going on that there's more error at the larger values of x. The effect of outliers, an outlier of course is any observation that lies outside the overall pattern, and an influential outlier is one that if you take it out it changes the results considerably. So let's look at this example for bone strength. So here's our original data, and let's say we added an outlier in that bone strength study. We stick this number over here on the right. We stick that number in there. Notice how it changes the equation. The slope of the line was 0.9, and that changes it to 0.4 roughly. It changes the y-intercept pretty greatly. Our r and r squared value, which is how strong is our correlation, went from 0.9 or 0.9 for our r, went all the way down to 0.473 by that one single outlier. That one point, and it's not that far off even, you know, it's but it is over there. Everything changes for that one single number. So outliers are a big deal. They're always a big deal, but they're especially a big deal when we do regression. So there's two types of inference or significance tests we can do with linear regression. So we can do a significance test for the population correlation and a significance test for the slope of the regression line. All of these tests will be two-sided. So far we talked about the correlation between x and y in the sample, and that was our r. Remember, So again, R, the closer that is to 1, either positive 1 or negative 1, the stronger the correlation. And if it gets close to 0, there is no correlation. All right, so we want to ask the question: Is there a relationship between arm bone strength and non-dominant arm bone strength? And the way they say it is that independent in the population. Okay, so rho is called the correlation of the population. So it's the correlation between X and Y measured on every member of the population. So when rho is 0, it's like, I don't know if you know anything about the Greek alphabet, but rho, we talked about how rho in Greek letters are population estimations, and R in alphabetic letters, R and X bar and S are all sample related numbers. So again, R is our sample, and the equivalent in the Greek alphabet of the letter R is the letter rho. And it looks like a P without the little leg on it. So R and rho are very similar in the Greek alphabet. Just like S and sigma in the Greek alphabet, our equivalent of S is the Greek letter sigma. So anyway, when rho is 0, there is no association in the population, and X and Y are independent. So when we say that they're independent, it means that exercise is independent of cholesterol level. So what you might find is exercise could be independent of how much electricity you use in your house. Right, there should not be any relationship between that, between how much exercise you have and what is your electricity usage. Those two things are independent from each other. There is no, these two things stand alone from each other. And so the null hypothesis is to test that population correlation is 0. So our null is that rho is 0, X and Y are independent, in other words, not correlated. And our alternative hypothesis is that rho is not equal to 0, which means that they're not independent or they are dependent and they are correlated. So we do this test statistic T, which is R times square root of n minus 2 over 1 minus R squared. And it has a T, n minus 2 distribution where degrees of freedom is n minus 2. And it's a two-tailed t-test. The p-value is less than alpha, we reject the null. P-value is greater than alpha, we fail to reject the null. Same thing that we did in every other t-test. So we have just a new test statistic here. All the other rules of how we apply p-values still apply. So to perform this test with SPSS, we need to look at the correlations output. Right? So we see that we get these 3 steps. It shows how to do this in SPSS, follow these 3 steps, and it gives us this table. So it gives R, our estimate for the population correlation, and here's our p-value right here, the p-value for a two-sided alternative hypothesis. So we do our test statistic T is 7.67. Our null is that rho is equal to 0. Our alternative is that rho is not equal to 0. And with a T of 7.67, you use the t-tables. If you went and looked that up, you would get a p-value of 0.000, which is less than 0.05. So we reject our null. And so at the 5% significance level, we have evidence that dominant and non-dominant arm bone strength are correlated. All right? They're not independent of each other. If one goes up, it looks like the other goes up. So the inference for the regression line, the model's assumptions. In linear regression, the explanatory variable x is quantitative and can take many different values. So we can think of the different values as defining different subpopulations. So what we're saying here is for everyone that has a non-dominant arm bone strength of, say, 15, there's a bunch of those people. And if we create a population of those, we're going to get some variation. And they're just trying to say that these numbers, as they go out, this is really best demonstrated here by this graphical visual from the textbook, to say that for all these values of x, if there's a arm bone strength, say here, of 13, then the distribution of that can be normal, and then there's a normal distribution for another value of x and a normal distribution for another value of x. So or instead of this arm bone strength example, think of something maybe more relatable. This is all the people whose height is 6'5", and then we'll plot their shoe size. So there's probably some people that have pretty small feet and they're 6'5". There's not many of those, and there's probably some that have really gigantic feet and they're 6'5". But most people just have that, whatever that common size foot is for somebody 6'5", and that's probably like a 13, maybe a 14. And then you got guys like my roommate in college who was, I think, like 5'10", and he wore like a size 13 shoe. So there's people over here at this lower height, and there's not many people that have feet that big when they're they're not that tall. But every place you pick your explanatory variable, there's going to be a distribution of y that goes with that. And so it's like a bunch of bell curves turned up in three-dimensional space. And the equation of that line is the slope that goes through each of those means of those normal distributions. Kind of a complicated thing, but this is how the derivation of the formulas that come afterwards are found. But I think this visual is much better than the slide before it, where we have a bunch of words to explain what we're trying to say. So we're going to check for assumptions. The scatter plot y versus x. So we'll see if mu y equals beta 0 plus beta 1x. Again, we're back to using Greek letters. Remember that Greek letters is population-related stuff. So if the data are aligned, if there's a linear pattern, assumption 3 is established. Residual plot. Let's see if check if the values of y. That's what we talked about. That residual plot. If the numbers are all kind of evenly balanced on either side of the x-axis, then we're good there on the residual plot. And so the normal probability plot for the residuals just is to check that y is normally distributed. All right, so if we meet those assumptions, then we're good. So here's the residual plot, which we talked about. The numbers here are on either side. There's some up here and there's some down here on either side of the 0 line. And then the normal probability plot for the residuals is this. It's kind of like a quantile plot that we've talked about. So you have that, and it's your they should follow that straight line, and they roughly follow that straight line, which means that the data is normal. Assuming the conditions for the regression model are met, we can perform inference on for the slope of beta 1, and we'll use SPSS for this. So the question we want to answer is the regression coefficient non-zero in the population, or do we have a linear relationship? So our null is that beta is 0, and our alternative is that beta is not 0. Again, it's a two-sided test because it's not equal. Everything we're doing in this section, and same with ANOVAs. Recall that, remember about ANOVA, everything was a two-sided test. So here's the button clicks in SPSS to do this. So we've talked before, we've been doing compare means, and we did general linear model for two-way ANOVA. We're coming down here to regression, and we're going to do linear regression. And you got your non-dominant arm and your dominant arm bone strength. And so you're going to put dominant as the dependent and non-dominant as the independent. And then we click on our statistics button, and we say we want estimates, the confidence intervals, whatever your confidence level is, and you can do a model fit. There's several other things here. You can do descriptives. We've done that before on these things. And then we're going to say plots. When you click on plots, you can say that you want a normal probability plot there. And then we're going to do a save. You can do, we're going to click the unstandardized predicted values, unstandardized residuals. You see all these little button checks we're going to do here, and that's under the save option. And this is the output that we get from SPSS. So we get all these values here. So there's our R value, which we saw on Monday's lecture, and R squared is the 0.819, and the standard error of the estimate. This is the estimate model for the model standard deviation sigma. So we've talked about standard error of the estimate as being our estimate for sigma. It pops up this ANOVA table. We won't look at that. And we come down here, and this is where we get B0 and B1, which tells us the equation of our line. And then we have our T value down here, and our P value right here. And down here we have a confidence interval, and the confidence interval does not contain 0, which means that the p-value was less than the level of 0.05. And another cool thing here is that you can also take B1 divided by S, the standard error of B1, and that's how you get your T. So if you take this 0.936 number and divide it by the 0.122, that's how you get T. Just for a fun little fact in case you wanted to know how that was calculated. And also, after you do this, what happens is back over in your SPSS data worksheet, it will come in here and populate columns with these different values. So this is our predicted values for the response variable y hat. This is all the y hat numbers. And I could jump back 10 slides, I'm not going to, but remember we did this in a table earlier. There was the x's and the y's and then the y hats. And then we had a fourth column, we talked about the residuals. There's that column for that. And then these are all the prediction intervals, because remember what we're saying here is for a non-dominant arm strength of 15.7 that has a interval, confidence interval of 13.8 up to 21.03. This was all those little normal curves stacked in 3 dimensions on that visual that I showed. This is showing what is the intervals and the width of all of each of those normal curves for each of these different x values over here on the left side. All right, so it's trying to give you all that information. So this is the lower, and this is the upper, and that's what the L and the U mean there at the top. So the significance test for the slope is the regression coefficient non-zero in the population, or said another way, do we have a linear relationship in the population? And again, we saw that our t was 7.665 and our p-value was 0 for a two-sided test. And so at the 5% significance level, we have evidence that the slope in the model is different from 0. All right, and that's how we would state that. Again, this beta 1 is the slope. So when you're doing inference, which type of hypothesis test to use? So we have to decide what we're trying to look for here. We use beta 1 if the words say slope or regression coefficient. All right. If we use rho when we're talking about correlation or independence, and if it's either beta 1 or rho, we say linear relationship. So again, the correlation and independence is all about, is this thing correlated to the other? All right. Is there a relationship between exercise and cholesterol level? That's what rho is all about. And beta 1 is the thing that says, is the slope or the regression coefficient going to be 0 or not 0? And so, again, that's the difference between beta 1 and rho here. And since there's some variability involved in using a model created from sample data, prediction interval is better than a single prediction. All right, so we have all those prediction intervals that were popped up there in SPSS. So if we collect data from different samples, the values of the y-variable will probably be different for the different samples. So if you went out and found a bunch of people that are 6'4" and you asked them their shoe size, all we're saying is you're going to get different answers for the shoe size. And a prediction interval is an interval used to predict a future observation y for a given value of x. So it has the expression y hat plus or minus t times the standard error of y hat. All right, and so it describes how that's calculated, and we'll use SPSS to calculate these. So again, this is how you get that interval. If someone is 6'4", I'm 95% confident that their shoe size is between 11.2 and 14.7 or something like that, right? That's what we're talking about there for that one particular value of a height. And so you can see right here, this again for this bone strength, they picked this line. There's a 95% prediction interval for a future y observation corresponding to x equals to 20. So if when someone had a non-dominant arm strength of 20, we can predict that their dominant arm strength is somewhere between 17.7 and 25.2, or 95%. That's a 95% confidence level of that. And so here's a scatter plot. These are for the 95% prediction level intervals. So here's our original data with our green line showing our best fit line that goes through there. And all we're saying is these blue lines here are our prediction intervals to say that all the data is going to be somewhere between those two lines all the way down. It's another way of think of this as a top-down view of that picture of all those bell curves in 3 dimensions kind of scattered out on a line. We're looking down at the top, from the top of the bell curve here, and we can see the tails of the bell curve of those little blue lines. It's another way to think about what that is. All right, so that's all we have for this lesson. Again, this stuff is not going to be on the test that you're going to take on Monday, so don't sweat about trying to understand it over YouTube with me, because I probably moved pretty fast, and I did move fast because it is YouTube, and you can pause, rewind, and go back and watch what I said again if you didn't understand it. So I'll try to take some time to go over this and, of course, answer any questions about it. Maybe I'll spend a decent amount of time a week from Wednesday after our test to hit some of the high points of that before we start our next lecture after the test. So again, a reminder just to get ready for the test. Just take that practice material that's in Brightspace, practice it, come ready for questions. On Monday, I'm going to work a lot of examples in class. If you are able, at 11:30, come to my office hours and walk 3090. You can also go to the exam review session at 4:30 to 6:30, held by the TAs. And again, the location of that is in Brightspace. I don't know it right off the top of my head. And so I hope you guys have a great rest of your week, and I look forward to seeing you all on Monday, the day of your exam too. So can't wait to be back and see you guys.